Good morning, good afternoon, good evening, everyone. Welcome and thank you for joining the call. My name is Alain Minelli, Marketing Manager, Europe and North America for Trinseo's ABS, SAN, and polycarbonate. During the next hour, we're going to discuss how to optimize performance and achieve greater customer satisfaction from the ABS resin that you select for your applications. This topic is something we felt could be of value to the marketplace because A, there is a significant difference in ABS material determined by its production method, and B, this is something that's often overlooked. For those of you unfamiliar with Trinseo, we are a global materials company, a supplier of plastics, latex binders, and synthetic rubber. We are a large organization with a global presence. At the same time, we are flexible and agile in our service model. We specialize in customizing solutions for our customers, and that's a key differentiator of ours in the marketplace. We produce different plastics, which I'll discuss briefly on the following slide. We have 16 manufacturing sites, we are in 25 countries, and we have 2,200 employees. Next slide, please. We are vertically integrated with some of the feedstocks that we use to produce our plastics. And we are also a compounder that provides custom solutions to meet specific customer requirements. Here's an overview of our straight from the reactor plastics business. Our portfolio of brands consists of polycarbonate, polystyrene, ABS, and SAN products. Today, as I mentioned, we're going to talk about ABS, which is a material Trinseo has been producing for over 4 decades now. We use a proprietary technology for our ABS, which is a continuous polymerization process. We produce ABS in the US, Europe, and China. China is our newest location, where we began production during the second half of last year. Next slide. I want to move into the main part of our presentation and introduce to you our presenter, Mark Vreys. Mark is our resident expert of ABS resins, and he's based in Terneuzen, Holland. Today, he's going to share the two methods of producing ABS, the more common emulsion method and the alternative mass polymerization process, comparing the two and discussing the benefits and applications of each. ABS, as you might know, is a very versatile material found in a variety of applications, including the furniture industry, the transportation industry, recreational vehicles, health and fitness equipment, kitchen and bath, and signage. We hope the information you see today is insightful and clarifies a few points for you. Before I turn the floor over to Mark, I want to mention that we will be holding questions until the end, but please feel free to submit them throughout the presentation by using the question field at the bottom of your screen. Mark, the floor is all yours.
Alain, thank you very much for this introduction. To the audience online, I say hello, welcome. Thank you for joining this webinar. And let's now start with the agenda. I will talk about the mass polymerization versus the emulsion polymerization process, highlight some injection molding and extrusion applications and the corresponding ABS resin attributes for those, and then go more in detail in those attributes through a comparative study of a Magnum high-impact ABS versus a high-impact emulsion ABS. And this for the attributes lot-to-lot consistency, coloring, UV stability, thermal stability, gels, purity of the product, volatile organic compounds, and finally the melt strength. So let's first start with the polymerization process, and I'll first highlight the proprietary mass polymerization process of Trinseo, which is also named as a solution polymerization process. And in this process, we start with a mixture of polybutadiene rubber, styrene monomer, acrylonitrile, and they're all brought together and mixed into a solvent. And this solution is then pumped into a fast reactor of a series of reactors that are interconnected. Now, in this schematic, it is simplified, represented as a single reactor. So the polymerization of styrene and acrylonitrile starts in this first reactor by increasing temperature and in the presence of an initiator, and continues further downstream through the series of reactors until completion in the last reactor. The final step is then the removal of the residual monomers and the solvent in the so-called devolatilizer. And then we move the ABS polymer stream into the finishing section, the pelletizer, resulting into Magnum ABS granules. Magnum, Trinseo's brand for mass ABS. This mass process, as you can see from the picture, is a continuous type of process. And because of that fact, it has somewhat less production flexibility, so we are somewhat limited in the breadth of the portfolio that we can offer, but it has also some inherent advantages. These advantages are for sure the absence of any processing additives like emulsifiers, leading to a very clean and pure ABS product. And by the virtue of being a continuous process with, as you can see, very few process steps, it will offer a high lot-to-lot consistency and also a light color and a higher rubber efficiency, making Magnum ABS less sensitive to rubber degradation processes when the material is processed. Now we move into the emulsion polymerization process, and this is a clearly different process. As you can see in a first step here, there is the preparation of the rubber latex using emulsifiers, water, catalyst, and butadiene. The next step is then the polymerization of styrene and acrylonitrile in the presence of that rubber latex. And part of the polymerized styrene acrylonitrile is then grafted onto the rubber. And this grafted rubber so a broader portfolio of products is possible, but it typically has a lower purity due to the presence of the emulsifiers. Now, in this slide, I want to highlight the morphology difference between mass and emulsion ABS. And you see here two electronic microscopy pictures. And let's first focus on the picture on the left side, which shows the Magnum ABS. Now the light gray background, that's the SAN polymer matrix. And the dark gray spherical particles, they are the rubber particles. This darker color is the result of a sample pre-treatment process, which is called the staining. And this staining process acts specifically on the carbon-carbon double covalent bonds which are present in the rubber. And then in an electronic microscopy picture, they are then highlighted as darker gray zones. Now, if we look more into detail on the left picture, you can see that the rubber particles, they are fairly large in size and they contain many SAN occlusions. So there is styrene acrylonitrile polymer inside the rubber particles. This is an immediate proof of the very high rubber efficiency of the Magnum polymerization process and makes it less sensitive to rubber degradation. On the right side, we have the emulsion ABS, and you can clearly see that the rubber particles are significantly smaller and they do not contain occlusions. In the emulsion polymerization process, there is a higher control possible on the rubber particle size. And hence it is also possible to produce smaller rubber particles in an emulsion ABS process compared to a mass ABS process. And for those applications that are seeking the highest gloss levels, they will have more benefits in using an emulsion ABS. Now let's move over to the processes and applications thereof. Let's first start with ABS injection molding. I have here a simple overview of injection molding applications where Magnum ABS is used. We have some consumer electronics, office equipment, housings, remote controls, telephones. In consumer goods, we see some toys usage, music instruments and toolboxes. And in the home appliances, we have housings for air conditioners where Magnum ABS is used, and in large appliances for door handles and end and top caps and instrument panels, and for also in smaller appliances for the housings, Magnum ABS can be used. Injection molding is all about many colors. So a high lot-to-lot consistency, an easy and efficient self-coloring, or clearly wanted attributes, as of course is also high gloss and good gloss retention after UV exposure, and addition color stability after UV exposure. Second process is ABS extrusion. Let's have a quick look on the applications here. Now, in ABS extrusion, you have two segments. You have sheet extrusions and you have edge bands and profiles. And the main difference is basically the width. Sheets are wide, edge bands and profiles, those are narrow. And in the sheets, you have several applications downstream. They are most of the time we talk about ABS PMMA co-extruded films for furniture applications, or ABS PMMA co-extruded sheets for vehicle exterior, like the tractor example, the engine hood, the rooftop, the wheel arches. In transportation, interior panels can be made from ABS extruded sheet. Automotive interior parts, we see here also roof boxes for automotive. Of course, ABS PMMA is very popular in sanitary equipment, also somewhat in the advertisement industry. Travel, we see luggage cases, and also the use for doors, inner doors, and sometimes also outer doors. Edge bands and profiles, they go of course into the edge bands for furniture applications, and we also see profiles in white goods for large appliances. Now, before I move into the attributes for ABS extrusion, I want to have a quick word about the channel to market, because there is some extra complexity in the channel to market compared to injection molding. One can roughly say that about 90% of the extruded sheets are being thermoformed. So the primary process in this channel to market is sheet extrusion. And the sheet extruders gives then or sends the sheets to a thermoformer, and there happens the secondary plastics process, where the extruded sheet is formed into a part. And the thermoformer sends then that part to the brand owner, who then assembles it into the end product. From there it goes then either directly to the end user or mostly through a retailer to the end users. If we focus on the primary process first, so the sheet extrusion, there are many important attributes for this extrusion. Both sheets and edge bands are offered in a very wide range of colors. Hence, easy and efficient self-coloring are important attributes of the ABS. Good lot-to-lot consistencies will avoid color dosing corrections, and they will enhance productivity and reduce scrap. Now, the sheets, they can be mono-extruded for basic applications, but as I already hinted, often they are co-extruded. And the co-extruded layer adds additional features to the sheets which the ABS cannot offer. As you can see on the right side of the slide, PMMA co-extruded layer will offer you gloss and scratch resistance. ASA can offer outdoor weathering performance. A TPU can give a soft touch feel, and the matte ABS layer can give you, of course, a matte surface appearance. In extrusion, there is side trim, and clean scrap is typically reused and regrinded back into the core layer of the sheet. Therefore, a very good thermal stability with retention of color and color properties is important, will be an important attribute. A good color retention upon UV exposure is relevant as well. And ABS resins that are pure and low in volatile organic compounds, they will avoid unpleasant smell during extrusion, but they will reduce also odor at consumer level, which is of particular importance if you talk about vehicle interior. If you look now shortly into the secondary process, and remember there is first extrusion and then secondary thermoforming, then there are some specific ABS resins attributes that are important for thermoforming. It's of major importance that the surface quality of thermoformed parts is very nice. There should be a complete absence of surface defects. So it is very important for the ABS that the unmelts, so the so-called gels in the ABS resin, should be as low as possible. Thermoforming, often we talk about large, fairly complex parts with high draw ratio, and that way may result in wall thinning. So a higher molecular weight ABS will offer a higher melt strength, and a higher melt strength will give you better thermoformability and a better wall thickness distribution of your final part. Obviously, like in ABS sheet extrusion, UV stability is relevant, and a pure product with low levels of volatile organic compounds, as already mentioned, would be beneficial for interior type of applications. Trinseo offers 4 standard grades, and you see here a chart with on the vertical axis the Sharpie impact strength notched, and on the horizontal axis there is the melt flow rate. And these 4 grades are Magnum 3904, which is a high impact rate for extrusion. Magnum 3404 is a medium impact rate for extrusion, and Magnum 3513 is also a medium impact rate that can be used for extrusion, can also be used for injection molding of not too complex parts. The true injection molding grade is the Magnum 8391. As you can see, it has a high melt flow rate, it is medium impact, and it is in addition specially designed to achieve a high gloss. So it has small rubber particles. The 3 other grades do not give you a very high gloss. Now we will move into the comparative study. And most of the comparative measurements that I will show will be the Magnum 3904 directly in comparison with a high impact emulsion ABS of a similar impact performance and of a similar melt flow rate. In the graphs, when I refer to Magnum, I mean Magnum 3904. If I refer to EABS, then I mean the high impact emulsion ABS. If I refer to EABS1, EABS2, then I refer to medium impact ABSs, all emulsion ABSs sourced from Asia Pacific. So the high impact emulsion ABS and in some cases the medium impact emulsion ABSs that I will show are referred to as EABS, EABS1, EABS2, and etc. And they're all from the Asia Pacific area. On the picture on the left, you see again an electronic microscopy picture of Magnum 3904. You see the fairly large rubber particles with the SAN occlusion, so very efficient use of the rubber. On the right side, you see the high impact emulsion ABS. Rubber particles are smaller, thus that product will have a higher gloss. Rubber particles are very dense, so there is a less efficient use of the rubber. Now let's move into the attributes, compare them one by one, the mass ABS process of Trinseo versus emulsion ABS process. First attribute is the lot-to-lot consistency. And the run sizes of Trinseo's process, they are quite big. And the run sizes are 400 to 1200 metric tons. And typically they are a factor 10 bigger in run size than typical EABS batch type processes. This will inherently lead to a very high shipment-to-shipment consistency, as a series of shipments often will originate from the same run. So in between these shipments, a customer will not have to do any color master batch adjustments, and that will reduce his risk for scrap. The second attribute I would like to talk about is coloring. Now, Magnum ABS has a much lower base color than Emulsion ABS, which is clearly more yellow. As you can see on the picture, left side Magnum, right side Emulsion ABS with a higher yellow base color. And thanks to the lower base color, it is easier for Magnum to color it into lighter colors. And on this graph, I represent here the color as a B star value on the vertical axis. And the higher the B star value, the more yellow the appearance is. And what we've done here is we have added 4% of a white master batch to Magnum and also to the Emulsion ABS. And that white master batch contained 50% of titanium dioxide. And at the same white master batch dosing levels, you can see that the Emulsion ABS is 2.5 units higher in B star value. So clearly more yellow. And it needs up to a factor 3 more of white master batch dosing to bring the Emulsion ABS to the level of Magnum. This graph shows a similar picture, but now I've added 2 experiments. We have added a fixed amount of optical brightener. With an optical brightener, you can give your sample a brighter and a lighter appearance. But even with adding an optical brightener, the message is the same. It is even so that the Emulsion ABS with 4% master batch with optical brightener still has a higher B star value than the Magnum with 4% master batch without optical brightener. Now this will have a direct impact on the cost to make final parts. If I assume here a cost for titanium dioxide of almost $3 a kilogram, then if I move from 4% master batch to 12% master batch to get to the same final color emulsion versus Magnum ABS, we are looking at over $100 extra cost for coloring for the Emulsion ABS. Now, the extra dollars is not the only disadvantage. There is also some loss in physical properties, as you can see in the second column of the table, where we did some falling dart impact tests, and you see there is a 15% reduction in total energy measurement. So there is some loss in impact due to the addition of extra master batch, coloring master batch. And also, as titanium dioxide is a kind of mineral, your density will go up as well, and it's not neglectable. It's about 9%. If you're looking at weight savings, then 9% is for sure not neglectable. There is another risk in using high amounts of master batch, and that is risks for surface defects. The picture on the left side is an electronic microscopy picture of a cross-section of a sheet right through a surface defect. You see this wave at the upper side of the picture. That is in fact the surface of the sheet. And the surface showed a local deformation due to an inclusion. And when we analyze this inclusion with elemental analysis, which you see on the graph on the right side, you see a major peak of titanium. And you see in the middle, and you see on the left side, there is oxygen. So clearly you can say this is very likely titanium dioxide agglomerate due to the too high usage of pigment dosing. Now we move into another attribute for the ABS. We move into UV stability. And this graph here shows the evolution of the delta E value here in the vertical axis when we expose ABS specimens to a so-called QUVA accelerated weathering tests over time. And the QUVA simulates more indoor solar exposure, and the delta E, you can see that as a numerical value that expresses the total color change versus the original color before submission to the accelerated weathering test. And the higher the delta E is, the higher the discoloration perception that you will see. And one can easily conclude here, if you compare the values at 300 hours of exposure and 150 hours of exposure, that the emulsion ABS ages twice as fast, or the mass ABS ages 50% slower. So in practice, this means that you can reduce the usage of UV absorber in theory with 50% for Magnum ABS versus emulsion ABS. Also, that has some impact on cost. If I take a standard UV absorber for ABS, which is in the direction of $30 a kilogram, and about 0.3% of level into Magnum ABS is sufficient for indoor applications, well, then it means you have a surge cost for emulsion ABS of about $80 a ton for the final part. Something extra on UV stability. Now we move from QUVA to this case is QUVB weathering, which is a more stringent UV exposure test as it simulates more outdoor accelerated conditions. And there we see that the Magnum ABS ages about 30% slower than emulsion ABS. So again, in theory, you could reduce the amount of UV absorber in comparison to emulsion ABS with about 30% in case of bulk loading into the ABS. Now, for outdoor parts, if they are based on extrusion thermoforming applications, then it is more cost effective to put the UV absorber into a cap layer. For instance, a cap layer of PMMA, or to use ASA as a cap layer to protect the ABS. Now let's look a little bit more in detail what happens now with the ABS if we expose it to UV. And let's break up the slide in two parts. Please focus first on the left side where you see the electron microscopy picture, and we focus first on the picture on the top on the upper left. And this is a cross section of an ABS part before exposure to UV light. And the blue line here on top, that represents the surface of the part. And remember, the light gray, that's the SAN matrix, and inside the darker gray particles, those are the rubber particles. Now, when we expose the ABS to UV light, then we move to the photograph below here. The blue line again represents the surface. And if you look very close, there is this region here where it seems like the rubber particles are gone. But they are not gone. They're still there. They just became invisible. Now, why did they become invisible? Remember, to make the rubber particles visible in electron microscopy, we use this pre-treatment process. Recall that? I call that the staining process. And the staining process acts on the double bonds that are present in the rubber. Now, because of UV exposure, these double bonds are gone. The high energy of the UV light starts to cross-link the rubber and destroys and consumes all the double bonds. So the staining process cannot happen anymore. And that's why the rubber particles are not visible anymore, but they're still there. So in effect, you have there, in this case, a layer of about 10 microns thick of completely cross-linked rubber particles. So that layer will act as SAN, as a brittle layer. So not only you are causing loss in mechanical properties because of embrittlement of the outer layer of your part, but you're also causing some yellow bodies during this cross-linking process of the rubber, which causes coloration. If you look very carefully, you will still see some black dots in this upper layer where the rubber particles are fainted. These are the pigments that we use to color the parts. If you now move to the right side, here you see an infrared spectrum. In pink, there is the infrared spectrum of the surface of the part that was not exposed to UV. And in red, you have the infrared spectrum of the surface that was exposed to UV light. And there are two distinct peaks appearing. There is this peak appearing here at 1725 reciprocal centimeters. You see this red peak is appearing. And this is typical for the carbonyl functionality. And this carbonyl functionality is due to photodegradation of SAN. Second, more to the left side, you see this peak here appearing between 3,200 and 3,500 reciprocal centimeters. And this is typical for the nitrogen-hydrogen stretching vibrations for amides. And also these are formed during the photodegradation of SAN. Now, the photodegradation process of SAN causes also the formation of yellow bodies, leading to color changes, and next to that, it also leads to the reduction of the SAN's molecular weight, which then will also lead to loss in mechanical properties. So that is what's happening with ABS after exposure to UV. Now let's move to the next attribute, and that is thermal stability. Thermal stability is an important attribute for injection, molding, extrusion, especially for extrusion, because there are also always significant amounts of regrind that are reused during the extrusion of the sheet. In this slide here, we show the difference in thermal stability between Magnum and emulsion ABS. And you see here a series of glass vials numbered from 0 to 6, and they represent different regrind passes, regrind and re-extrusion passes. And 0 is obviously the starting point, and 6 is after 6 regrind passes. You can see that the color change is to yellow is much more apparent with emulsion ABS. If you watch carefully for vial 5 and 6, you even see a red shine coming in. And if you compare pass 6 of Magnum with pass 0, so with the start color of emulsion ABS, you could roughly say 6 passes of Magnum gives you the starting color of the emulsion ABS. Hence, the Magnum is more suitable for high regrind loadings or higher regrind loadings compared to emulsion ABS. That will require more color corrections and of course then more cost for pigment. Now we move to the following attributes, which is gels. ABS should be preferably low in gels. Now, why are gels so important? I'll try to explain that in the next slide. Let's first focus on the left side of the slide where I show sheet extrusion. Now, gels can cause aesthetical surface defects because these gels, they don't melt during the extrusion. And if you extrude a sheet or a relatively thick sheet, the gels may be in the sheet, in the core of the sheet, and they're not visible because they are in the core of the sheet. But if you thermoform them, you get a tremendous wall thickness reduction, and then the gels pop up and they will cause a surface defect, an aesthetical defect after the thermoforming process. If you look to the right side of the slide, there we talk about film extrusion. So the thickness is a lot thinner, then gels may be visible or more likely visible after the extrusion process. And they will become even more visible when you would slightly thermoform the film or lacquer the film, or if you laminate it on a wooden board for furniture panels, where you have then very straight surfaces, and they will immediately show the surface defect when a gel is present. Gels are less an issue in injection molding compared to extrusion thermoforming, because in injection molding often the wall thicknesses are higher and the gels are then buried in the mass and the core of the wall. How do we control gels at Trinseo? We have a special device for that. You see an overview picture on the left side. We take on very regular intervals, we take samples from our production, and then we extrude those into a thin film. And on the right side of the picture, you see the film passing through a light source and a camera, and that camera is connected to computational software, and this software makes different categories of the cell sizes. We have the very small ones, the small ones, the medium ones, and the large ones. And for each of these categories, the software computes the number of gels that we have per square meter of film, which we then can calculate back per kilo of resin. And obviously, the medium size and the large size gel categories are the most critical for extrusion thermoforming applications. And I will focus now a little bit more on those two gel sizes. Let's start first with the medium gels. And I have here a relative count on the vertical axis per square meter of film. And for magnum, then is obviously 1. And you see then that for the various emulsion ABSs tested, so the EABS is the high impact emulsion ABS, and then the 3 others are medium impact emulsion ABSs. There are about 2.5 to 6 times more gels, more medium sized gels that we found in these emulsion ABSs. So the risk for surface defects due to medium times gels is significantly higher with emulsion ABS. If we move now to the large gels, the difference is even more dramatic. We are looking at a factor 10 more, even 50 more in presence of large gels for some emulsion ABSs versus magnum. That means if you are in critical extrusion thermoforming applications, it is wiser to use then magnum ABS versus one of those emulsion ABSs. Next product attribute is the purity of the product. And I show here 2 differential scanning calorimetry experiments. On the left side, we are looking to magnum 3904, and we have done here a scanning from about room temperature to almost 250 degrees. And then we see 1 changeover in this experiment, and that's the changeover for the SAN matrix. Of course, there would also be a changeover for rubber, but that would then be on the negative temperatures. If we move to the right side of the slide, we see the DSC experiment on the emulsion ABS. And indeed, at about the same temperature, around 105 degrees, you see also a changeover. This is the changeover of SAN. But in addition to that, there are 3 other changeovers, around 45 degrees, 70 degrees, and 128 degrees. These are changeovers of impurities present in the ABS. Now, a DSC experiment is not a fine experiment. It's pretty brutal. So you would need already close to 1% of an impurity before it would be visible in a DSC. So in this case, we can roughly say there is 3% of non-ABS product in this emulsion ABS. And you would prefer your ABS as pure as possible. I could exclude here one impurity, which is in this case additionally intentionally added. That's the one at 70 degrees. This is a mold release agent, a lubricant that is intentionally added for a specific reason. But the two other 2% impurities, they do not contribute to anything the ABS has to do. We move to the next ABS attributes is volatile organic compounds, or VOCs. We have expressed them here as microgram carbon per gram of polymer, and we see about a factor 4 more VOCs in the high impact emulsion ABS from Asia Pacific versus Magnum 3904. If we compare the same experiment to a series of other emulsion ABSs, the message is fairly similar. Also, other emulsion ABSs from the Asia Pacific region have significantly more VOCs than Magnum, almost a factor 2 to 4 higher. We move into the next ABS attribute, which I call melt strength. Melt strength is very important for thermoforming. Let's first look at the left side of the slide, where I will try to explain the melt strength measurement. We start from a rectangular test specimen that we heat to a temperature of 155 degrees, and then we will pull this test specimen with a force at a fixed rate. And we continue pulling, and at a certain moment the specimen will start to show necking, and finally it will break. And the force at which it will break, we call that the melt strength. And the melt strength is of imperative importance for thermoforming. I'll try to explain that with a picture on the right side of the slide. You have an extruded sheet. That sheet gets heated in the heater of the thermoforming station, and then it moves to the forming space in the thermoformer, and there it's first blown or sucked into the bubble prior to the actual vacuum forming step. And when the sheet is blown or sucked into the bubble, it is obvious that necking will happen in the wall of the bubble, and the necking in the side wall, the circular side wall of the bubble, will be higher than on the top or the back of the bubble. Now, the higher the melt strength is, the more resistance that you will have against the necking. The less necking that you will have, the better the wall thickness distribution over the entire part of the thermoformed part will be. Now, melt strength is directly related to molecular weight. And the Magnum shows about 20 to 30% higher molecular weight than the various emulsion ABSs from the Asia Pacific that we have tested. There is a second element that plays a role in the melt strength, that is the purity. If you have 2% or 3% of non-ABS impurities, they will not contribute to the melt strength. On the contrary, they will reduce the melt strength. They are just sitting there as a kind of plasticizer for the polymer matrix. So high molecular weight and higher purity, they are both beneficial for melt strength, and the melt strength is beneficial for a homogeneous wall thickness distribution after thermoforming. This brings me to the conclusion slide, where I would like to highlight short the advantages of the mass polymerization process. In the attributes, we see high lot-to-lot consistency, which would benefit in less scrap. The mass polymerization shows a low base color and a very efficient coloring. And for very light colors, we can assume cost benefits of roughly $100 a ton on the final part. There is an improved UV stability because of the higher rubber efficiency. So there is less cost of UV absorber. We have seen examples of up to $80 per metric ton on the final part. The better thermal stability allows for more efficient use of regrind, causes less scrap, less color correction, therefore less costs. We have clearly seen that there are less gels and smaller gels and less larger gels in the mass ABS. That will improve surface quality, especially after thermoforming. It's less of an issue in injection molding applications. Lower VOCs will give, especially at consumer level, less odor in vehicle car interiors. Mass ABS shows higher melt strength through higher molecular weight and higher purity, and that can result in improved wall thickness after thermoforming. So I come here to the end of the presentation, and I open the floor to any questions.
Thanks a lot, Mark. That was a great material. We had a number of questions that came in during the presentation. And yeah, so just let me pick the first question. I'm currently using an Emulsion ABS, and I'm thinking about trying a mass process. What would I need to do to switch from a processing perspective, and will I experience a visible difference?
Okay, thank you for this question. We have to make a distinguishment between an injection molding application and an extrusion application. So I presume it's here going about an injection molding application. Obviously, you will have to adapt the level of pigment. You will have to use less pigment, especially if you are working with lighter colors to get your color match. If it's darker colors, there is still a benefit of using less pigment, but it will be less outspoken. If you have a very high gloss requirement, then it's important to go to the Magnum 8391 because that's the standard grade that we have that can achieve high gloss, because I explained that in general the mass ABS process results in somewhat larger rubber particles versus the emulsion process. Another possible difference, but that depends very much on the quality of the tools. In the mass ABS polymer, we do not put a mold release agent. Often in emulsion ABS polymers, a mold release agent is present, and that can help for demolding the parts. But that's only of importance if you don't have correct designed tools, or if you work with old or worn out tools, then this may be of importance. That can be handled by putting the mold release into the color master batch. In some rare cases this is done, but in most cases this is not necessary. So to summarize, you need less pigment, so you will have to do a new color match. You need to think, is it a high gloss application or not? If it's high gloss, then it's the Magnum 8391 to be used. And in very rare cases, there may be a need to include a mold release into the coloring master batch.
Great, thank you, Mark. I'm going to pick another question that came in. The question is, what are the cost implications between using mass ABS and emulsion ABS, not just UV whitening agents added as was discussed already? And you discussed, I guess, other advantages like the pigment load. Are there other things that you can bring to our attention that can impact the total cost of using a mass ABS versus an emulsion ABS?
The greatest benefits next to coloring and cost of UV additives, they are in extrusion thermoforming applications where the surface quality is of major importance. It's all about managing risk. If you use Magnum ABS, due to its extremely low content in gels, the risk for surface defects at the secondary process owner, the thermoformer, or even further downstream in the channel to market process at the end consumer, the risk for surface defects is a lot less, is a lot smaller. Let's take the example of furniture foils. When you extrude as an extruder your furniture foils, this happens obviously at fairly high speeds because the foils are very thin. And it's not so straightforward to do a total control of your films. That's hardly impossible. But in case of Magnum ABS, you don't need to be worried that much because the risk for surface defects is very low, especially in this process for furniture films, where it's only at the very end, at the kitchen, at the consumer itself, when after installation of the kitchen, the furniture foil, the protective foil on top of the furniture is removed, and only then the surface defects are visible. So they're only visible at the consumer level. And if then the consumer complains, you're talking about very high cost because you're so far downstream channel to market chain. So managing that risk is a much easier exercise with mass ABS, and there are potentially great cost advantages there.
Okay, thank you. And another question that came in is about for which emulsion ABS, for which application would emulsion ABS be appropriate? Because we were just talking mainly about mass ABS and advantages, and there is somebody wondering for what application emulsion ABS can also be used.
If you seek the highest gloss, you're better off with emulsion ABS. Let's recall the graph, Sharpie impact versus melt flow rate. Mass ABS offers 8391 high flow, medium impact, specially designed for high gloss. So there, the usage for these conditions, if you have a medium impact, high flow, for these conditions, mass ABS can work. But for the higher impact, for the lower melt flow rate grades, we cannot offer the highest gloss. So if you're looking for a high impact grade that you want to injection mold, then you're better off with emulsion ABS. If you're really looking for the very, very highest gloss, also at higher melt flow rates, you're better off with emulsion ABS. Emulsion ABS with the smaller rubber particles has also a broader or a more forgiving injection molding process window to achieve high gloss. With mass ABS, you can achieve high gloss with the right grade, with the right type, and the process window will be a bit more narrow.
Okay, thank you, Mark. We have time for just one last question. So let me ask you this one. If I understand correctly, it looks like with a continuous process, I will have greater cost savings with lighter colors because of the whiter base color. What kind of benefits will I see when moving to a mass process for dark colors? Or is an emulsion process fine?
For dark colors, obviously the pigment cost benefit will be less. But for some, I would say, how you would call it, medium dark colors, if you think about certain red colors, you always have to overcolor the yellowness, the yellow base color of the emulsion ABS. And for some certain types of red, this can become difficult. And you may not match the perfect color that you want. So that will give you some restrictions. The darker you go, the less the cost benefit will be, because it's easier to make. Black and dark blue and dark brown, it's easier there to mask the yellow base color of emulsion ABS.
Okay.
If you add on top then the thermal stability, if you think about extrusion and using high amounts of regrinds, then you will see again benefits for the mass ABS, because the more yellow, and remember there was also some reddish shine coming in after multiple regrind passes, that will become always more difficult and difficult to overcolor. And finally, you have only the really dark gray and black colors left, where it's very easy to overcolor.
Thank you, Mark. Yeah, makes sense. There are more questions, but we will have to answer them offline. So I'm now going to close out the webinar. But before I do, let me put up the contact information. So next slide, please. And I want to thank you again for joining the call, and mention that following the call, you will receive a copy of the presentation. At this point, yeah, thank you, and have a good day. Trey, back to you.
Elaine, thank you so much. A big thank you to Mark and Elaine for that really great and informative presentation. As we did mention, there will be a copy of the slides and video posted to the UL Prospector Knowledge Center within the coming days. So do check your email for that. We will be sending out a copy that way. We also do encourage you to check out some of the other great webinars that Trinseo has on the Prospector Knowledge Center. But again, wanted to thank our audience today for attending, and have a great rest of the day.